Hi, and welcome to today's webinar, the fifth in our series of webinars. Today's webinar is entitled Rising to the Short Chain Removal Challenge. I'm Connor Walsh, the CEO of OPEC Systems. I'm joined today on the sofa by Peter Murphy, our President,
G'day guys.
and Dave Burns, our Chief Scientist.
Hi guys.
And then all the way from your territory in Boston, USA, we have Mark Salvetti from CDM Smith, who will come in later in this presentation and give us a little bit of an overview of the work that they've been doing in the US.
Hey, Mark.
Hi Mark,
Hey, Mark.
how are you?
Hey everyone.
We fantastic turnout. We've got over, I think we're close to 400 people on this webinar, which is great to see. Clearly a lot of interest there. We want this to be a really interactive webinar. So if you've got questions, in the bottom right-hand corner of your screen, it's a little chat box. Feel free to put any comments in there, any questions in there, and we will come back to those questions at the end of the webinar. We expect the webinar to go for about 60 minutes with the Q&A session at the end of that. If you haven't seen the first four in our series of webinars, encourage you to go onto our website and have a look at the four webinars that are there. The website is epocenviro.com. That will give you a real flavour for our PFAS remediation journey that we've been on over the last couple of years. Now you're probably wondering if I've got that right. EPOC, OPEC, yes, I have got it right. What we have done is globally we have rebranded our Enviro divisions and works to become EPOC, which stands for Emerging Pollutants of Concern. The rest of our business continues to trade as OPEC Systems, but certainly the environmental side of things is now trading globally as EPOC. Exciting news, OPEC Systems celebrates its 30-year birthday this year, which is, I think, a really good milestone for any SME to achieve 30 years in business. But I think more importantly for people watching today, that just gives you an indication for the last 30 years, we have been creating intelligent environmental engineering solutions for our clients. The rough agenda that we want to go through and cover today is, there's been a lot of stuff going on since we've done our last webinar over the last 12 months. So we're going to have a quick look at those current projects. We're then going to take a deep dive into PFAS short chain removal, what short chains are. We'll then cross across to Mark Salvetti from CDM Smith. They've been doing a lot of work with the SAFF 40 in the States, and so we're going to get Mark's warts and all view of just how that's performed. And then we'll come back to Sydney. We'll take you out to Western Sydney to our manufacturing facility that we're just setting up at a place called Emu Plains. And then we'll go straight into your questions and answers. So hit us up with as many questions as you can during this webinar. Pete, last 12 months, it has been a challenging 12 months we've still had border restrictions. Sydney went through a whole series of rolling lockdowns. At one stage, I think we were locked down for 10 consecutive weeks. We've had quarantining when you've travelled overseas, but still in that last 12 months, we have managed to achieve an enormous amount. So maybe just bring our viewers up to speed with that.
Sure, thanks mate, good to be back. Yeah, busy year. I mean, certainly challenging for everybody on the call, I'm sure. It's been tricky, but I managed to travel for about 5 months of last year. I spent 7 weeks of that in hotel rooms in isolation and got quite used to my own company, but I'm happy to say we made some really good progress over the last 12 months or so since the last webinar. So probably the highlight for us is the Oakey plant, which was the original SAFF plant, which is up in Queensland. That was a 3-year trial project that concluded earlier this year, and happy to say we've had our contract extended, so we're no longer on like a pilot trial. We're actually a fully fledged grown up water treatment plant operating on site. We've had the volume of water we're treating through that plant quadrupled. It hasn't had any exceedances in those 3 years. It's processed about 25 to 30 million gallons, I suppose, over that time. And we've reduced that down to about 12, maybe 14 gallons of concentrate now. So it's been performing exceptionally well, and I guess a testament to that is the is the contract extension, which we're really happy with. And then similarly at the Telge site in Sweden, where we put our first containerised SAFF system that went on a landfill. And I remember arriving there in the depths of winter last January, terrified that this project was going to be the death knell for us. And here we are, where that plant's also treated about 25 million gallons of really complicated landfill leachate water. And I know Helena from Envitech has just had that contract extended for another 2 years. So it's at the very least going to go on to treat another couple of 100 million litres. So yeah, great. They're very exciting advances. And then we've set up our manufacturing plant and lots going on around the world.
Well, and I guess the other thing that in that time we've actually got more units that are actually out in the field, and we've got a list of units that are currently under manufacture and will be in the field shortly. So do you want to give us a bit of an overview of that position?
Yeah, absolutely. So, again, we go back a year, we had that one plant in Sweden. We've now had, got another SAFF 40 unit on a landfill site in Sweden. We've just finished a big trial in the UK, doing some complex industrial wastewater over there. That was in conjunction with Cornelsen, who are in partnership with Envitech, our European distributor. Very interesting project at very high levels. We've got projects coming up in Spain, in Germany. We've got 2 systems just landed in Sweden that are just getting commissioned by our staff over there now. So, and another bunch on back order. So plenty of projects out of Europe. In the US, you'll hear from Mark Salvetti a bit later, but CDM Smith, who we've been working with for a few years, did a fantastic full-scale field trial in the eastern states recently on a site. We've got a trial coming up in Massachusetts on landfill leachate. What else we got? Oh, the big news is we've got a contract with the Minnesota government to provide a SAFF system up to Minnesota. So these guys, of course, are trustees of some of the big settlements that have occurred up there with some of the PFAS contamination. And so just out of Minneapolis, we've got a plant going on an extended field trial to treat surface waters and various other types of PFAS impacted waters. And then back home in Australia, we've got another plant going to the guys at the Shoalhaven City Council in New South Wales, where they've got a very interesting kind of closed, like circular economy approach, where they're taking their landfill leachate water, they're putting it through the SAFF, they're recirculating that through a glass recycling plant, and then that water comes back. So the SAFF sort of sits at the centre of this quite complex waste management process. So excited to see that a bit closer to home as well. So yeah, like projects happening everywhere.
There's lots going on, and certainly the Minnesota one I think is very exciting, because I think where there is the first sort of technology that's being used in that site there. So that's exciting. I thought it might be beneficial just at this point in the webinar for those viewers who aren't familiar with the surface active foam fractionation technology that we've developed, and we've been spruiking now for 5 webinars and for a couple of years. I thought it might be just to show a very short animated presentation, which just gives you an overview of how that technology works. I think you do the background noises in
Easy, mate. No, it's very basic, but if you haven't seen the concept before, it just gives you a bit of an overview. So
give you an overview.
If you're already into it, forgive the simplicity, but we just thought it might be a good starting point.
Surface active foam fractionation, or SAFF, is a proven method to remove PFAS from water. SAFF works in 3 distinct stages. During the primary fractionation stage, PFAS molecules are separated from water using the power of air. At the secondary fractionation stage, the PFAS molecules are concentrated. And at stage 3 of their fractionation journey, the PFAS molecules are hyperconcentrated. Once the molecules are hyperconcentrated, they are ready for destruction. And in the meantime, the clean water can be safely returned to the environment. Air bubbles concentrate PFAS. Their use in SAFF presents a highly effective and environmentally responsible way to strip PFAS from water.
Excellent. So very, very simplistic overview there, but now
Tree.
now we're going to get into the real nuts and bolts of what we're here for today and get into some of the chemistry and more stats and figures. But what we're here to talk about today is the short chain removal from PFAS, and just maybe we start at the beginning of this webinar by just exploring what short chains are and why they've been problematic for remediators like ourselves and our competitors to remove from PFAS.
Sure, mate. I can kind of kick that off. We'll dive into the chemistry of the short chains a little bit later, but in a broad sense, I mean, I'm never quite sure what the final number is, but somewhere I think between 6,000 and 10,000 different PFAS compounds out there, and short chains make up a reasonable amount of those. And so these, for us, short chains are typically the C4 and C5 chemistries, the C6 carboxylates, the ones where the Langmuir constant is a little bit lower, which kind of means they're a little bit more soluble. They're a little bit more slippery in a remediation sense. So I don't really know that it matters too much what the remediation technology is. Certainly with the absorbent-based technologies like GACs and resins, with our technology, those shorter chain compounds, then I mean PFBAs and PFBSs and PFPEA and even PFHXA, they become a little bit trickier, particularly those PFBAs. They break through really quickly. In the sorbent-based approaches, you get bed volumes, kind of, 2,000, maybe 20, 30,000, but they do break through quite quickly. They result in sort of having to replace media, in having to deal with higher volumes of waste. And what's happening is, as regulatory environments around the world, we kind of started with PFOS and we shifted to PFOA and PFHXS, but now a lot of the regulatory environments are starting to at least consider, if not incorporate, removal of short chains. And so for us as a foam fractionator provider, we had to look at how we could either integrate our technology as part of a treatment train to remove these short chains, or whether we could do it in our own right. And so the short chains are sort of constantly there now. We find them, they tend to migrate ahead of the plume. They get large uptake in aquatic plants and terrestrial plants. We have a lot of challenges in stripping them out. So we've really, and particularly in the last 12 months, turned our head towards how we can deal with them.
I love that concept of a slippery chemical, and I think if my chemistry teacher had used those sorts of descriptive words, I would have stuck with chemistry rather than becoming an accountant.
I'm sure there's better.
Well, that brings us to, I guess, the breakthrough announcement on short chain removal from SAFF systems.
Yep. So we have looked at various ways, and Dave, I think we'll probably go in a little bit later into the specifics of absorption isotherms and how they work. But the bottom line for us is we've utilised the combination of the physical, mechanical properties of foam fractionation, and by that I mean the geometry of the vessel itself, the way we're introducing air bubbles into the equation. We're bringing them in to maximise saturation through helical structures and circulation patterns within the tanks, the size of the air bubbles we're dealing with, just playing with the veracity of the air bubbles. You've got these fine lines between too much air creating emulsions that really is not helping you, and not enough air, so hence minimum efficacy in PFAS removal. So playing with those characteristics, and also we've been looking at various kind of chemical amendments and ways to improve short chain uptake.
So I guess we've now got a bit of an overview of how we're doing that. Dave, you've been in the trenches for our PFAS journey, and you've been looking at short chain.
Day one he was there, weren't you, mate?
Used to have no grey hair.
Maybe take us back through our history of short chains and give us a bit of an overview there.
Yep. Well, first, it's great to be back on the couch, even at this early hour in the morning here in Sydney. Yes, the the CDM Smith short chain performance data, certainly big news and a noteworthy breakthrough. I guess from the early days in the lab, 2015, 2016, all the way through to 2018, and including the first SAFF 40 field trial work up at Oki in 2019, the short chain treatment has always been front of mind for us, even though the regulation and criteria at that time was focused on PFAS, PFOA and PFHXS, these being the main chemicals listed or nominated for listing on the Stockholm Convention's Persistent Organic Pollutants Register. But at this time, and up till this time, we only had solutions for the long chains. Then we advanced to our first field trial in Sweden, SAFF 40, January 2021, where we were asked to manage and remove PFAS to below 50 nanograms per litre, and also monitor the other Swedish 10 compounds from this very large landfill leachate catchment that was characterised by complex chemistry, excessive foaming, to the point that if you didn't manage it, it would flood the columns.
It was crazy.
With foam. And there was a much broader suite of PFAS at this site compared to the Oki 3am light water contaminated site here in Australia. And it was actually, this site was the first time we actually noticed much better stripping of long and short chains, most likely due to all the other non-PFAS amphiphilic substances present in the leachate feed. And then to now, with this our first SAFF 40 field trial in the US, partnering with CDM Smith, who's leasing and managing this project. This is the first time where we're seeing like this new and exciting news on short chain removal using a full-scale SAFF platform that removes these short chains just using the onboard control system of the SAFF. And I guess a lot of upfront preliminary work done by Drs. Charles Schaefer and Zoom Nguyen from the CDM Smith Research Lab in Seattle, who did bench scale feasibility studies.
Yeah, those guys were great help.
Because Pete, you've talked us through some of the mechanics and changing things and working with different sized air bubbles and so forth. And I know earlier, I guess yesterday, we were talking about just trying to look at the air bubbles as being that absorption media, and I think that's important that people sort of understand.
Yeah, it is, mate. I mean, I guess in trying to explain foam fractionation technology, which for some viewers might be a fairly new concept, others are starting to get used to it. I remember turning up in the States actually at an ESTCP conference in 2019 and nobody had heard of it. Physical separation was a kind of a, it seemed like I was a crazy guy. And I came home and I was like, oh, no one knows about it. But anyway, I think we have managed to get the word out, and that air-water interface is becoming increasingly understood as a really great medium. But what I'd ask viewers to think about is when you're used to sort of granular activated carbons or ion exchange resins, these are absorptive mediums. They have a certain number of available sites. Those sites can allow PFAS materials to bind to them in an adsorptive sense. And they have a certain capacity which once filled requires either replacement or regeneration. And if you can think of the air bubble, it's actually no different. It's really an absorptive medium for PFAS, just like GAC and resin are, but you have this benefit of infinite supply of air bubbles, and this very convenient characteristic that air bubbles rise to the surface of a water body, and where the PFAS accumulate as a foam, because they're naturally foaming products, although as Mark will take us through later, sometimes even foaming can be a challenge, but nonetheless the air bubbles are sort of taking the products up, and rather than this infinite supply, and they're free to access, and they have kind of almost an infinite capacity in a practical sense to absorb the PFAS molecules in the sort of concentrations we encounter them.
Well, I like that slide that was on before, just demonstrates how the molecule likes to hang out in air bubbles.
Yeah, look, you got this kind of hydrophilic tail, which is a characteristic of most PFAS compounds, and then you've got these functional head groups that are hydrophilic hydrophobic tail, I should say, and then a hydrophilic head group. And so that surface of the air bubble is actually a very comfortable, to use another simplistic term, environment for PFAS compounds to reside on. It's where that Gibbs free energy constant is managed to its best ability, and so you find that PFAS will preferentially transition onto that interface.
Yeah, I love it. And then we just lift it to the surface.
Free ride to the top. And
free ride to the top, gather it in a bit of foam and then extract it. So very, very simplistic technology, but works very effectively. Just on that, you talked about changing where we can introduce different sized air bubbles, introduce additives at some different stages during the process and so forth. With that, does that mean that the SAFF units that we've got out in the field, do we then have to recall those to retrofit them?
No, mate. I mean, we've been for 30 years, I guess, building fluid transfer systems and management systems for fuels, for contaminated waters, for hydrant waters, all sorts of stuff. And so when we're doing these complex engineering solutions for fluid movement, we're always got an eye to redundancy. We don't want to sell the client a product that's redundant in 12 months' time, and we've taken a very similar approach with SAFF. And so really right back to the very first SAFF 001 that we saw up there at Telga, we've been building them for, but not with, a lot of the adaptions that we've since made. So we had extra apertures and penetrations in the vessels for integrating different types of sensors. We ran comms lines through that we didn't know what we were going to use them for, but we had them there. We overspec'd the onboard PLCs and NUCs, the small computers that are on board, so that they could accept additional data streams. And so we've really gone right back to SAFF 001. As new ideas evolve, we're able to retrofit them in there without having to recall them. They're fairly easily implemented in the field. So the reality is SAFF 001 can actually do everything that the latest SAFs can as well.
Nice. Yeah. Well, the accountant in me likes that we don't have this huge cost of recall, and I'm sure our existing clients are excited about that as well. I think now's probably a good time to bring our guest speaker, Mark Salvetti from CDM Smith into the webinar now. So Mark is, CDM Smith have been an early adopter of this technology. We've been working with them for a couple of years now, and Mark and his team have had a SAFF 40, and without wanting to steal your thunder, Mark, I'll let you present. Mark's actually a senior project engineer with CDM Smith and has been pretty heavily involved since that SAFF 40 arrived on the east coast of the States. So Mark, welcome, and I'll let you take over.
Great, thanks, Connor. Audio sounds good?
Excellent, sounds perfect. Sounds like you're in the room with us.
All right, great. Well, good afternoon, everyone. I'll be talking about our full-size SAFF pilot. Let me get my slides up. We ran this at our site from late September to early December of 2021. Let's see. Okay, there we go. So I'm just going to run through some background on our site, what our technical approach was. We ran some bench scale studies as well as the full scale pilot study in the field, and then we'll talk about our findings from the standpoint of PFAS removal, volume reduction, our ability to remove short chain compounds. A couple photos here on this initial slide. You can see the large air stripper there at lower right. This site has legacy chlorinated solvent contamination in groundwater. Our clients not responsible for that. The prior site owner actually operates that air stripper. It runs at about 1,200 liters a minute, 300 gallons a minute. And then you see that photograph at the top. That's the SAFF 40 on our pad, ready to go. There we go. So we have chlorinated solvent contamination in groundwater, but our client actually had an accidental release of AFFF from a site drain line. This impacted site groundwater about 300 feet from the nearest extraction well. But over time, the operation of the extraction well has drawn that PFAS towards the extraction well, and we're starting to see PFAS in the air stripper effluent, about 500 parts per trillion. Our client was required by the regulators to do something about it. They needed to move quickly, and they were required to add treatment to that air stripper effluent to prevent the discharge of the PFAS. The air stripper effluent goes to the local river under a discharge permit. So we scrambled and we installed a temporary ion exchange treatment system to remove the PFAS. We've got two 200 cubic foot resin vessels in series. It actually works really well from the standpoint of removing our PFAS compounds. However, our site groundwater coming out of the stripper has very low concentrations of dissolved manganese. And they seem low. The vendor thought they were low, but they've been causing us problems in the resin. We get a crust forming on the top, so we get this cementitious layer of resin and manganese forming on the top. Also, fine particulates that precipitate out inside the resin bed. This has caused a lot of operational problems. We need to shut down and remove that cement layer off the top. We've had to backwash our resin vessels, and we've had to replace resin much more frequently than was expected, because we end up with high pressure drops, and all the backwashing damages the beads, and we end up with high pressure drop through the units. So our client had a lot of interest in the SAFF unit because it doesn't suffer from these limitations associated with the dissolved metals. So we brought a SAFF unit out to our site in September. Just a quick snapshot of our water chemistry. Just from the shape and colors on the two pie charts, you can see how similar the site groundwater on the left is to the air stripper effluent on the right. About 11,000 total parts per trillion in groundwater, mostly PFNA, over 7,800 parts per trillion. Our air stripper effluent, about 500 parts per trillion, again, mostly PFNA. And this just shows how we're drawing that source area plume towards the extraction system. So initially we collected site groundwater and air stripper effluent, shipped it to our pilot study bench scale system in Bellevue, Washington. We ran it there to try and establish operating parameters, evaluate how well it foamed, see how well we could remove PFAS concentrations. And then we took that information and we translated it into the field pilot, where we ran both water types. We wanted to see what the operational settings were for each water type, evaluate how and if we could remove the short chain compounds, confirm our concentration reduction, and look at energy consumption, but our overall cost, because the client was interested in replacing the ion exchange system potentially with SAFF units in a full scale scenario. We'll just talk about the results from our bench testing. Here you can see some photographs of our bench test system in Washington. What was interesting about this water was that we had trouble getting it to foam at all in the bench. Both the air stripper effluent and the source area groundwater, which had the high PFAS concentrations, we didn't get much foaming. We had a very difficult time achieving any significant PFAS reduction running it through the pilot study, the bench scale system. Eventually, we ended up having to add amendments to enhance that foaming. Once we did that, the system worked great. We saw multi-log PFAS reduction at the bench scale. We were able to establish a good PFAS mass balance. We were able to show the amendment we added could be removed. That was important. It was readily removed and concentrated with our PFAS. And we saw an 80 to 200 times concentration factor across two stages, a primary and a secondary fractionation. So once we evaluated those bench results, we took what we learned and we translated it to the field pilot. We were curious whether we'd have the same issues with foaming or lack of when we ran our site groundwater through the SAFF 40, look at what kind of volume reduction we were getting through the system, what needed to be done to remove short chain, again, verify the amendment was needed, and then if needed, that we could remove it, and understand what their operational parameters could be if we chose to go full scale, what that was going to cost, how many units we would need, and so forth. A couple photos of the installation. The unit was shipped from Australia to Philadelphia, and then it was trucked to the site. We've got a crane here lowering it into place on our treatment pad. There in the background, you see the white shipping container. That's the container that actually holds our temporary ion exchange system. Both ion exchange vessels are inside that container. We had all our needed infrastructure here: power, discharge, piping. We could draw water from the airstripper effluent, which goes to the ion exchange system in the background. So we were able to just load it here on our gravel pad and go. So initially, we started out with the airstripper effluent. Our regulators required us to demonstrate that we could remove PFAS to our discharge limits before we could run the unit and just discharge to the river. So we had to run in batch mode. We ran batches of primary fractionation and took that treated water and stored it in storage tanks on site until our lab data could come back and we could show to the regulators, look, we've achieved our discharge standards. Now for us, we were being regulated only on PFOA and PFOS, about 5 and 6 parts per trillion, respectively, in our discharge before we could go to the river. We looked at different variations on aeration energy, basically aeration rate, duration, and we also evaluated optimization for short chain removal. We adjusted these parameters. We looked at adding amendments at different times during the process. And ironically, the very first run that we had actually was able to achieve our discharge standards. But we collected all of our batch data and we selected the best parameters, ran them by the regulators, and they approved us, and it allowed us to start running continuously on that airstripper effluent. We ran that way for 8 hours a day, then shut down, then restarted the next morning. Now, as you saw in the animation, there's multiple steps in the SAFF process. So our primary fractionators were able to achieve our discharge standards. So the water came in, it was fractionated in those primary units, the treated water was just discharged. The foam that came overhead was collected, and once we had enough volume, we ran our secondary fractionation. We ran a secondary fractionation about every 3 hours of continuous runtime. About 6% of each of the primary fractionation vessels ended up going overhead as foam and ultimately was treated in the secondary fractionators. The photograph here on the right, it shows what you would expect to see in the hood, in the top of the secondary fractionator. You see a good head of foam. It's actually being drawn out through the top and accumulated in another tank for later tertiary fractionation. Interestingly, we had trouble getting these secondary fractionation runs to work, running on the airstripper effluent. It sort of behaved more like we saw on the bench. You know, initially, airstripper effluent in the primaries on the SAFF unit actually performed better than we saw on the bench. The secondary fractionation was reminiscent of what we saw on the bench. We actually had to add small amounts of amendment to enhance the foaming and get this tall head of foam to form so that we could draw out the PFAS from the secondary fractionation. But ultimately that worked very well. We were also able to optimize to remove short chain compounds. So my next slide is going to have a table that'll show our analytical results. So let's start in the middle here. The green columns represent SAFF 40 runs on our airstripper effluent with about 500 parts per trillion total PFAS and no significant optimization to try and enhance short chain removal. We were focused just on PFOA and PFOS removal. We had no amendments, and we actually were able to consistently achieve our discharge standards for PFOA and PFOS. We saw between 82 and 98% removal, consistently achieving our discharge limits. PFNA was our main compound, 90 to 99% removal. Overall, about 73% removal of our total PFAS. So our 520 parts per trillion. On average, we were discharging about 140. We needed that amendment to successfully perform the secondary fractionations, but it was fully removed. It concentrated with our PFAS. There was none in our effluent. So then we began working, as I mentioned, on short chain enhancement, adjusting aeration, durations, adding amendments. It's critical that you add it at the right time. Adjustments to the way we collected and consolidated our foam. And that was super successful. Over 96% removal of our regulated compounds, 99.5% removal of PFNA, 97% overall removal, and you can see a significant improvement in our short chain removal. PFBA, without the enhancements, we were only running about 12% removal. We managed to get it up to 36%. Not awesome, but still a lot better. And overall, we saw a real improvement running with the optimization for short chain removal. Once we ran through our airstripper effluent, we started collecting source area groundwater. And this was a slower process because we only had a single monitoring well that we could draw water from. So we had to run only in batches. We didn't have a continuous 300 GPM flow of water that we could take a slipstream from to run the SAFF unit on. But we still ran the same way. We filled our primary fractionators. We looked at different aeration energies, durations, how we consolidated the foam. We ran with and without amendments to see what our performance was on not just short chain, but all PFAS removal, and then what we could do to enhance it. So here's our results with our source area groundwater. Here again, this water behaved very much like we saw it behave in the bench. We had very little foaming in both the primary and the secondary fractionation stages. And that's reflected in our data here in the three middle green columns. We only were able to get about 50% reduction of our total PFAS from 11,700 down to about 5,800 parts per trillion. We never could achieve our discharge limits for PFOA and PFOS. We were only getting 50 to 60% removal of those compounds. As was the case with the airstripper effluent, we weren't getting very good we weren't getting very good short chain removal. We never were able to meet our discharge limits. And as you see there on the right-hand side, our removal efficiencies were down significantly, certainly compared to the airstripper effluent. So to treat this water, we really needed to optimize. So again, we went back and we ran additional runs with different aeration rates, durations, foam collection, and amendments. And here again, we saw a dramatic improvement when we optimized for the short chain removal. Over 98% removal of our regulated compounds. So we got PFOA from 400 parts per trillion down to 1.4. 99% removal of PFNA. So we went from 7,800 parts per trillion down to 30. 98% overall removal on this high concentration groundwater. And we saw a big jump in our short chain efficiency. We went for PFBA went from 20% up to 40, and similarly PFPEA jumped up. So this was a really successful demonstration, we felt. It really showed that we could treat our site groundwater, this high concentration water, as well as our airstripper effluent, meet our discharge standards, but even go beyond that and really enhance our ability to remove short chain compounds. Few conclusions from this run. So as I mentioned, we showed that this unit can successfully treat our site groundwater up to 400 times reduction in some of our individual PFAS concentrations. We did this performance in both dilute water from the airstripper effluent at about 500 parts per trillion, as well as the concentrated groundwater. We were able to optimize the performance of the unit and increase and enhance the short chain removal. We saw no impacts of the dissolved inorganics. There was no fouling, there was no scaling, as we expected. So that was a great improvement over the ion exchange performance. We do feel that, this piloting step is still critical. We did learn quite a bit from our bench scale, but we're not confident yet that we can go from bench and make a direct leap to a full-scale system and be confident that we can achieve the discharge standards. Case by case, but right now we're recommending the pilot step right after we do the bench. We saw a volumetric reduction of about 90,000 times. So we treated about 1 million liters of site water, 260,000 gallons. And from that, we got about 2.8 gallons of tertiary fractionate. That water had about 5.5 parts per million of total PFAS in it. We did need the amendment, but that really wasn't an impediment. It greatly enhanced our removal. It all was removed and concentrated with our PFAS, and we had non-detect in our effluent water to the river. We had to continuously demonstrate that for our regulators. So overall, we were very pleased with the performance, as was our client. We had some data gaps. There's some things that we want to look at more closely the next time we run the unit. We do feel we need the pilot optimization step still after bench. As we've been talking on this whole webinar, running it standard, running it without any attempt to enhance short chain removal doesn't give us a great short chain removal efficiency. However, we can optimize that significantly and greatly increase the amount of short chain compounds we removed. The amendments can be a little bit of a regulatory acceptance issue. We had to show to our regulators what we were using, and we had to show that we could remove it before we discharge it to the environment. Wasn't that difficult. We were able to show that. That's consistent both on the bench and here on the SAFF 40 full scale. We were able to show we could remove it. We did have some mass balance issues. Treating 260,000 gallons, that wasn't a huge volume when you consider the low concentrations of PFAS in this water. I think we had about 0.5 gram total of PFAS in our effluent water and our tertiary fractionate. We fed more than that. We know we didn't discharge any, or we discharged very, very little. So we're not exactly sure why we couldn't close the balance, but I suspect that we've got some PFAS clinging to various nooks and crannies inside the SAFF unit. We just have such little amount of mass that it's difficult within the analytical accuracy to capture it all. We're still working on the life cycle costs. And this isn't really a data gap, but a natural question is, okay, you got 2.8 gallons of tertiary fractionate. Now what? Well, we're busy treating it right now using electrochemical oxidation. We have a pilot size unit in our Denver lab. That water from this system that we collected is undergoing that treatment right now. It's been very successful. Unfortunately, I don't have permission from a client yet to start sharing those results, but it is very promising, and we believe that using that technology, there's a great potential that we will have no waste, that we can totally destroy the PFAS in that concentrate and have little, if any, waste stream to dispose of with PFAS. I've been going on a bit here. That's the end of my presentation. So certainly ask questions, but I'm going to turn it back over to our team in Australia.
Excellent. Thanks, Mark. And some great results, and appreciate your honesty in everything you've said. We have got a lot of questions coming through, and that's great. So please, if you can hang around until the Q&A at the end. I just looking at Mark's presentation, I'm wondering, guys, if we just go back and just do a basic overview of the principles of how SAFF works and how we're achieving some of these results. So Dave, do you want to?
Yeah, sure. I guess the first comment I'll make is that with the PFBA result, it's still, like Mark said, that where he's been able to remove 36 to 40% of it. In the future, I do think we'll increase that as we're able to continue to increase our knowledge on how to manipulate the absorption coefficient and also get access to new, more specific amendment chemistries that remove more of the PFBA and also other non-PFAS surface active chemistries. But the principles that sit behind being able to get more of the PFBA out, plus other surface active chemistries, basically this graph here. So with fractionation, it's all about the absorption coefficient, which I harp on a lot about. So it's denoted by the red line, which derives as the gradient of the absorption isotherm for any particular PFAS in a specific water under specific criteria. And it's this information that helps us decide if a specific PFAS molecule will be uptaken onto the all-important air-water interface. And that then determines whether or not we're able to strip out that molecule from the feed water to below the site adopted criteria. And I guess the key point to note is that because short chains have much lower absorption coefficients than long chains, it's a bit harder to do that. And this occurs because short chains tend to be much more soluble in the feed water. They have a much shorter dipole moment across the length of the compound. And it all adds up to mean that the short chains have a much smaller Gibbs-free energy saving by jumping onto an air-water interface of a rising air bubble. So that's the chemistry part of it. Then we add our SAFF engineering knowledge to try to add additional encouragement to short chain compounds which are in that group of low absorption coefficient groups, to try to push them onto that all-important air-water interface in combination with the new amendment dosing system we have in the SAFF as standard, to add an amendment at the right time in the right location for the right amount of time, which is why we think in the future we'll get even better PFBA stripping that Mark's just gone through, but also a whole range of other chemistries. And like we're even seeing now lots of questions and inquiries to Epoch Enviro. What else can you strip out of water besides PFAS?
And what else do you think we can strip out?
There's heaps of things. So the first one that comes to mind to me is all the foaming agents that are non-PFAS that are in F3 PFAS-free foams. So they still can do environmental damage if they get into an aquatic waterway. And a lot of those, they're going to foam. So it's obvious to use foam fractionation for that. There's microplastics in wastewater. So we've done some work with Scott Wilson's team at Macquarie Uni, where we loaned him and his team the Epoch Systems desktop SAFF apparatus, and they spiked in microplastics, and he was able to show that he could remove more than 95% of what he spiked. There's pharmaceutical active ingredients that are surface active in wastewater. So I think as people like Bresso and his team who have the intent to develop a absorption coefficient register for lots of surface active compounds, when that eventually becomes available, let's cross our fingers, that'll mean that practitioners of foam fractionation will be able to predict what SAFF will be able to do for PFAS and surface active chemistries.
And I guess just to jump in there, Dave, like what, in a kind of very simplistic way, so we're trying to play with the absorption isotherm to optimise the removal of these various surface active compounds, including PFAS. And so how do we play with that absorption isotherm? Like there's some really fundamental physical ways to do it. So, for example, salinity, the conductivity is a primary one. So more conductive waters, less soluble, we shift the position on the absorption isotherm in our favour, and we get better removal rates. Temperature is another influencer, pH is another influencer. We're also, as I mentioned a bit earlier, playing around with physical geometry. So we're by crowding in at the top of the tank, the foam layer that was spread out over a broad area is now spread over a narrow area, and we're able to harvest that foam a bit more efficiently. And different, just trying to find those optimal energy levels within the fractionator vessel itself, so that we can play with that absorption isotherm, get it in our favour as best as possible in a physical sense, and then look at what sort of amendments and additives we can include. And of course, the holy grail is moving towards these biosurfactants. And there's no point putting a chemistry, replacing one toxic chemistry with another toxic chemistry, and so you remove all the PFAS and you leave something that's problematic. So we've also got to prove that we're completely removing any compounds that are added.
And the additive could be site-specific. So we come up with the mixture. It could be balanced for pH, it could be balanced for electrolytes. It definitely could have a biosurfactant or some other type of surfactant in
additional long chains that provide some lift for the short chains.
And then the other thing to note is that we'll select what surfactant we want in there to either stay soluble in the treated water, in the case of a soil washing project where we want to continually reuse that to soak out and strip out PFAS from soil, or we might choose an amendment that reports out of the treated water into the foamate, because we don't want it in the treated water that gets disposed to the environment.
Depends on the receptor, doesn't it?
Yeah, it's all site specific.
I think, that gives us a good overview of just some of the principles there, and certainly the ability for the SAFF unit to be very, very flexible and be fine-tuned. And I guess the beauty of it is we can do a lot of that fine-tuning remotely as well. Look, the power of the rising air bubble, what we've shown is we've got a global solution where PFAS is encountered, which potentially will go on to other chemistries. We don't need GAC, we don't need resins. It's simply the air that is the absorbent material, effectively, that's taking that up to the surface, and we're harvesting it. And I think, from our perspective, we believe that's going to create a lot of demand, or at least we hope that's going to create a lot of demand for our SAFF units. And I think to that end, it's probably worth just showing our viewers, we have spent, in the last 12 months, we've spent a lot of time and energy in terms of trying to look at how we're going to be able to meet that demand. So we've established a new manufacturing facility out in Emu Plains about 12 months ago. And I thought what we might do is just
Western Sydney
for those who aren't familiar with Sydney's suburbia. And I thought what we might do is we prepared a video earlier which just takes us to that site, gives us a bit of an overview of our capabilities in the manufacturing going forward. So if we can just jump to Emu Plains, that'll be great.
Thanks, Connor. So here we are in Emu Plains at the Epoch Manufacturing facility that we've been setting up recently. Only about 300 metres from where I went to high school, so the wheels come full circle. We're here today, we're delivering a unit for our partners Alonia in the US, so this system will be heading off next week and it's getting wet tested today. Wanted to run you through a couple of things, mainly this fantastic facility which we've built. We'd realised a year or so ago that we really had to ramp up our production capability, and so this facility is all about that story. And we also wanted to take you through the actual quality control wet testing process we go through. So I'm joined today by Jeff Rowland. Jeff's our Global Operations Manager, and effectively, Rolly, you're in charge, mate. Once these systems are finished and the wet testing's completed, you make sure they make their way overseas?
Yeah, that's it, Pete. The story doesn't end when it rolls out the door. It's great to be here and see the facility now starting to really take shape. 6 months ago, we realised that we needed to get these units out to the market faster. Everyone was telling us that was a requirement, and so we acted on that. The project has gone fantastically well. Very proud of the team that have put the facility together, and now we're seeing those improvements that we were looking for coming to fruition. So it's exciting to then be able to have these units and to start setting up the support that the clients are going to need across the globe.
So for 30 years or so, we've been a fluid movement, fluid handling organisation dealing with fuels and all kinds of different fluids. And so the evolution to SAFF and the treatment of PFAS impacted wastewater is really not a big transition for us, but we have taken on a new basis of manufacturing in our agile system. So, mate, can you give us a rundown on sort of how that works and how it applies to the SAFF?
Yeah, so obviously, Pete, the global supply chain disruptions that everyone's been experiencing since COVID, joined our lives, means that you need to take a different approach to manufacturing. And Agile allows us to get all of our materials and equipment together to build very efficiently and with a high level of quality assurance, make sure that the units, when they deploy to our global SAFF supermarkets in all of our different regions that we support, have excellent quality standards before they leave this factory or any other factory, and then that the needs of the client and the value that we provide to the client through SAFF is maintained for the life of the actual unit.
So we talk about efficient production. What are we talking about through this facility here?
Yeah, so the SAFF can be built piece by piece by piece, or it can be built as components and then brought together very, very quickly. So by restructuring the way that the plant works, it allows us to have multiple teams working on different parts of the SAFF all at the same time, which then are brought together to the finished product, commissioned, and then out the door. Yeah. And that's the whole aim of the agile manufacturing process.
Brilliant. So with a capacity of up to 150 units a year, we think that'll meet the demand over the next couple of years, and then we've got the ability to take this exact agile platform.
That's the exact plan. Yeah, the regional support starts with operation and maintenance teams that can help client commission a unit, do repairs and maintenance should that be required, keep the unit completely operational, and that is supported by a remote telemetry service which allows us to make minor tweaks and modifications to suit the environmental conditions that the SAFF units find themselves in, and also the types of contamination that we're finding in the water, because it's such a wide spread.
Sure, so we might find it in groundwater, we might find it in leachate water, and the SAFF system kind of is able to work in all those different operating environments. It's a brilliant part of the unit. I mean, the purpose of today with the wet testing, though, is we're going to ramp the system up. Like we need to know the system's going to work. We'll go overseas and we accompany our units on each and every occasion to make sure they're functioning. But back here we do this wet testing process, which is just all about making sure, at the most basic level there's no leaks, but plenty of other systems. We're testing the onboard computers, the PLCs and HMIs. We're testing all of our sensors, making sure that there's obviously no leaks. A couple of new changes that I'm super happy with. So great bunding integrated now. We've got an improved level sensor capability. We've got the ability to flush the heads and the sensor lines automatically at the end of each process. So bit by bit we're learning, right?
Yeah, that's it. The whole process within EPOC's mantra is continual improvement. So as we find things that will make SAFF more efficient, that a client specifically needs because of their particular problems, then we make the effort to get those integrations right and continually improve the product and create value for our clients.
Yeah. So as we wet test, on this occasion, we start the units up. So we've got our two primaries and our secondary. And the idea is we will just fill these systems up initially with potable water, and then we just trial with basic surfactants just to make sure everything's functioning. So you can see the secondaries kicking off here, just checking right to the top of the level sensors that we're able to run that system. We aerate it, we pressurise it, and just make sure everything's running well. So looks great with the backlight there, but as the PFAS foam rises, it's drawn out of the top of these hoods and into the concentration tanks on the left. So some new designs in those tank banks as well, which is making it more efficient in the high foaming leachate environments. And as I mentioned earlier, various little tweaks that are helping us along the way.
Yeah, that's it, Pete. And the idea is to make sure that the units are supportable, that spare parts are readily available, that there's a team of qualified, capable technicians that can get in there and do preventative maintenance and reactive should something catastrophic go wrong.
Brilliant. Well, thanks, mate, for your time, and thanks, guys. We'll head back to Belrose now and jump back on the couch. Thank you.
Excellent. I love that commute, an hour and 30 minutes. We can do it in the space of a couple of seconds. So I hope that gives you a bit of an overview of just where we're headed towards in terms of the manufacturing capabilities. And I think it's important to note that what we are doing with that facility is very replicable. We can take that facility to Europe. We can take it to the States if we get bigger demand and so forth. So, Pete, I know for the last couple of probably the last 6 months, you've been very busy with your lawyer hat on. Working through some of the global distribution agreements that we're trying to put in place and had some success there. So
Have indeed. Yes, it's been an interesting 6 months of just working our way through contracts, but happy to announce we've now got a North American distribution agreement with Alonia. So Alonia, you might have heard of them, you might not have. They're a fairly new startup, but they're a very interesting company. They're backed by Battelle, the Bill and Melinda Gates Foundation, and Ginkgo Bioworks. And so they're very much focused on biotransformation, bioingenuity, to bring solutions for pollution remediation and management. They've got a bit of a long-term goal to develop a range of bio-based products. But where we found a really good alignment was that these guys kind of are looking at utilising biomimicry, and we've said from day one that this SAFF process is very much a biomimicry process. I mean, on the edges of lakes and oceans and so on, you always see this foam generated, and we're really just kind of taking what nature does naturally and we're optimizing that into the SAFF process. And so there was a really good alignment of values to bring us together, and also the team at Alonia is just a fantastic team of individuals who we're really excited to work with. So those guys will be looking after the whole North American presence for us. So we've got that arrangement signed, sealed and delivered, and we're going to kind of launch that at Battelle next month. And then in Europe, we've got our original partners Envitech, who were looking after the Scandinavian territory. Envitech are another interesting company. They're owned by Sortera, who's one of Scandinavia's biggest waste management companies, who are in turn owned by Nordic Capital in the way of the modern world. And so these guys have some really deep connections and really solid backing. And their intention is to bring SAFF into the entire European market. So they've been pushing really hard into the Dutch territories, into Belgium, into France, into Germany, and particularly into the UK, as well as back home in Scandinavia. So those guys are really working well over there, and so that agreement's just about across the line as well. So that was important. We needed to get that support to give our kind of customers in those territories confidence that they'll be supported.
Give us that global footprint. I think in the short term, just send any inquiries into us and we'll make sure it goes out to the right party. Hey, just before we get to the Q&A, because we are getting close to the end of the webinar, but just quickly before we get to the Q&A, if you're a viewer, you're watching this webinar today and you've got a contaminated site, I know we've been working on this sort of 3-step process of what we think people should do. So do you want to quickly step us through the 3-step process?
Yeah, look, mate, it's pretty simple. I mean, it's really founded on the idea that if people are going to invest in your technology, they want to be confident it's going to work. And so we have this 3-stage process, which starts with our predictability model. So on our new Epoch Enviro website, there's actually a form there that you can just fill in your details and actually input the SAFF concentrations at your site. It can be completely anonymous, and it generates a report that will tell you how we think SAFF is going to work. So we've tested about 40 different types of waters now, from RO regenerates to process waters to landfill leachates and groundwaters and surface waters and so on. And so we have an increasingly high degree of confidence about how SAFF is going to work in those different kinds of environments, and we can give you that indication as part of that service on the website. Step 2 is we've got bench scale testing systems. So that's broken into kind of 2 phases. One is SAFF has separation and concentration phases. So if you just want to see how SAFF works to remove PFAS from your water, we can just do with a simple 5-gallon sample or so, 4 to 5 gallons. We can run a test, generate a report, test before and after, and you'll see just how much of the PFAS and what type of PFAS is removed. Or we can do a more complicated test, which takes us about 7 days to do, where we run a series of primary batches and we generate a fomate, and then we fractionate that fomate to see what sort of concentration factors you can affect. And that's pretty important because you want to understand how much waste you're going to generate. So we have that benchtop testing capability. And then, as Mark advocates for, and I really encourage this, is we've got units in all the territories that can be engaged on trials on sites. Realistically, these systems do 40 cubic metres an hour, or maybe a bit less on leachate sites, but, it's high volume throughput, 10,000 gallons an hour. So within a few days or a week or certainly a month, you're going to be able to run as many tests and crossways and every which way to give you the confidence that it's going to work. And then, if the results from that field trial come back as positive as they have in the scenario with Mark, then you can move to the proposition of either leasing these units or purchasing them outright for the site and utilising our operation and maintenance and kind of site support and backup capability.
I think what I really like with that 3-step process is it de-risks it for the client, and it also de-risks it for us in that we're not putting a unit on site and going, okay, it doesn't actually deliver what we promised it would, which is great. We've come to the end of the sort of presentation side of the webinar. We're just about to jump into the Q&A, and we've got lots of questions there, and feel free to keep typing questions there. We'll stay as long as we want. We're going to get Mark back to answer some of those questions. Just before we go to the Q&A, just probably worthwhile pointing out, we are attending the Battelle Chlorinated Conference.
Good to be back face to face again.
Yeah, which is on May. I think it was postponed and cancelled a couple of times due to COVID, but it's on May 22nd to the 26th. We're a major sponsor. We're doing a presentation. We've got 3 poster sessions. We've got a learning lab. Our exhibit is 323, and on that we are going to have a bench scale unit on display. We'll be pumping water through it. Won't be contaminated water, I can assure you of that, but it will be there to show the principles and so forth. So if you are going to that Battelle conference, strongly encourage you to go and catch up with the team there. So Pete will be there, Dave will be there, and Jeff, who you saw earlier on the video, will be there. Unfortunately, I won't, but go and knock on the stand there.
Bring you back a present.
And please, if you wouldn't mind, that'd be great. If you can't stay for the Q&A, just relax. We will be sending out a link in the next couple of days, but please stay for the Q&A. There are lots of questions there that we're going to work our way through. If you have questions, more specific questions, please direct those to either Peter or Dave if they're SAFF related. If you just want to understand about what CDM Smith have been doing, just send those questions directly to Mark Salvetti at CDM Smith. Email addresses are up on the screen now. The other thing I'd probably encourage everyone to do is, just if you don't already do it, follow us on LinkedIn. We post a lot of stuff on there because it is a continually evolving market that we're in, and we're continually coming up with innovative solutions to some of these emerging pollutants of concern problems that are out there.
As much as we can.
Excellent. All right. Well, guys, thank you so much for your time. Mark, thank you so much. You've been a pleasure to host in the last 3 webinars.
Thank you, Mark.
Good on you, man.
Sure. Great. It's been great.
And
thank you.
Thank you to our viewers who have dialed in and invested an hour and a half of your time watching us. So thank you for that. Have a great day.
Thanks, guys. Have a good
Bye,
day.
everybody.
See you all.